Hello and welcome back to the course on Applied Econometrics. We have been talking about autocorrelation, and in the previous lecture we have seen what is autocorrelation, what is the consequences of having autocorrelation. So we really don't want to have a lot of autocorrelation in our model. But in order to identify if the autocorrelation present in the model is significant or not, we need to have something quantitative in our hand based on which we can take a decision whether to sort of say that the autocorrelation present in the model is significant or we need to do something about it. So let's say we have to do some tests. And for that, there is one test, that is Durbin-Watson statistic test, which is particularly popular. We sometimes, in abbreviation, we say DW statistic. So we use this DW statistic to predict, sort of estimate the extent of autocorrelation present in the model, and we have some decision-making rule based on which we say whether to say that the autocorrelation present in the model is significant or not. So let's go back to our previous lecture where we actually wrote down a AR1 process, and we sort of I sort of had an equation where we sort of estimated the relationship between the error terms of different period. So for an AR1 process, if the error term of tth period is ut, and if let's say the autocorrelation coefficient between the error term for different periods rho, and the error term in the previous period is ut minus 1. So this is how they're related. And let's say there is some innovation term, error term. So it's basically independent. It's independent of all the variables present in the model, and it is essentially IID, independent and identically distributed with a zero mean. So we can actually express ut and ut1 ut minus in terms of ut minus 1, that is a past period error term. Okay, so let's say that is how the errors are related in this process. Now we know that this is about the population, so we really cannot get the ut or ut minus 1 or even et, right? Because it is in the population, so we can never estimate that. What we can do instead, we can have some sample data to estimate something that will sort of be a representative of rho. Okay, so we can sort of estimate ut as ut hat, and then we have, let's say, some gamma, and then we write ut minus 1 hat, which is the previous period error term, you know uh, estimated value. And of course, when you are estimating this ut or ut minus 1, there is no question of having an innovation term here. Instead, what you can have is an intercept term, right? So the intercept term, let's say I write is a delta 0. Okay, and let's say I name this equation 2. Now if I want to write the null hypothesis for presence of autocorrelation for equation 1 corresponding to equation 1, so my null hypothesis is going to be, so null hypothesis, my H naught is going to be, the rho will have to be 0, right? So if there is no autocorrelation, that means the rho is 0. So by this period error term is not dependent on previous period error term, so this is end of the story, there is no autocorrelation. But if there is autocorrelation, so then HA, alternative hypothesis, is going to be rho not equal to 0, not equal to 0. I'm not saying if rho has to be greater than 0 or rho has to be less than 0. As long as rho is not equal to 0, either the two period error are positively correlated or negatively correlated, but there is some correlation. And if there is some correlation, so then that means there is autocorrelation. Okay, so that's going to be our null and alternative hypothesis. All right, so now we know that we cannot estimate rho, we have to estimate gamma. Now how do we estimate gamma? Now before I answer that, let me actually write down what is Durbin-Watson statistic in the first place. So I write dw statistic, and I'm going to write a formula for this, and this is equal to, let's say, ut hat. So I have estimated ut and ut minus 1 hat, that is the error term corresponding to this period and past period, and then I square them up. I basically take the subtraction between these consecutive terms and I square them up, and in the denominator I will have only ut hat and its square. Okay, now there is something you need to note when I actually sort of indicate the time period. So here I start t is equal to 2 to t, and in the denominator I start from t is equal to 1 to t. Why do I do that? Because I'm taking this subtraction here, So essentially, if I take t is equal to 2, so ut minus 1 hat is essentially going to be u1 hat, right? And whereas ut hat will be u2 hat. So essentially, I'm basically taking the subtraction for the two error terms corresponding to period 1 and period 2. Whereas since I'm taking t here, so from the very first term, or the term corresponding to period 1. So I will start from t equal to 1, right? T equal to 1 to t. So essentially you see that there is one term less here, okay? So let me actually, I'll just illustrate that how do we calculate Durbin-Watson statistic in a moment. But before that, let me write down how Durbin-Watson statistic is related to this gamma here, okay? So that's the thing that we are going to do with the Durbin-Watson statistic. So it is, the relationship is like this: Durbin-Watson statistic is equal to 2 into 1 minus gamma. I'm not going to prove it. So this is the relationship that we'll be using to sort of estimate the value of gamma. Okay. Now let me illustrate how do we actually calculate Durbin-Watson statistic with an example, so that will make our life easy. Now let me actually go to one Excel sheet I have. So let us look at the values of y and x. Let's say we have taken from some real experiment, or some real valued observations, and I have all these values of x: 56.7, 98.7, 89.2, and I have corresponding values of dependent variable: 20, 47, 34. Now what I do is I actually get this number on my stata, and I actually feed a regression equation. And what I see this is a very nice fit. R squared value is pretty good, and x value, the coefficient of x is going to be 0.41 with a constant term or intercept is equal to 0.7. Okay, great. So I got my regression equation, and I again go back to my Excel, and I have actually written down the regression equation: y is equal to 0.7 plus 0.41 into x. Okay. Now this y, the new y I got, this is essentially the fitted value of y, right? I got the fitted value of y. Now if I plot these values of actual x into this equation, so that is 56.7 into the equation, so I'll get 23.94 for the fitted value of y, whereas my actual y is equal to 20. For the next term, if we put x is equal to 98.7, so the fitted value of y is going to be 41.16, whereas the actual value of y is 47. Similarly, the next value will get the fitted value of y is 37.2, whereas the actual value is 34. Okay, so this way we get the y values, fitted value of y, from the equation, whereas the actual y is given. Now, how do we calculate the error? So we are already familiar how do we calculate the error. So essentially, you just have to subtract these two terms, fitted value of y and y, right? And if we subtract these two terms, we get this error term. So if we subtract 20 minus 23.94, so you will get minus 3.94. Similarly, for the second term, third term, for all the different terms, we get this error terms, right? So the 5.83 we get by subtracting 47 minus 41.167, and so forth. So this way we get all the error terms. Now if we go back to our DW statistic, for the numerator we have to take the difference between the subsequent error terms, right? So that means I have to take a difference between this 3 minus 3.947 minus 5.833. So if I take the difference and then I square them, now because both of them are having negative sign, if I square them, I'm going to get something like 9. It's going to be, close more than 9. So if I square this up, so I'm going to get something like 95.64. Similarly, if we take the second consecutive error term, so that is 5.833 and minus 3.272. If I take the difference, again they are having the same sign, so I add them up. Again, it is going to be slightly more than 9, and when I square it, so I'm going to get something like 82.9, right? Next pair, I get 3.27 minus 1.29, so there is a negative opposite sign, so it is going to be something less than 2 if I basically subtract this, and then I square it up, so it is going to be 3.89. So, and this way we get the difference, basically square of the difference of the error terms, okay? And this way we get all the values here. Now we have to, according to the Durbin-Watson statistic, I have to sum these things up. So I sum these things up and I get 205.338. Okay. For the denominator, I have to basically square the error terms and I have to sum this up. So I square this up 3.9 minus 3.9 and I square it up. I get 15.57, 5.833. I square it up 34 point something, and so on and so forth. I square this error terms up and I sum it up. So I get 56.66. Okay. Now, according to the again this Durbin-Watson statistic formula, I will have to divide this two, and if I divide this two, I get 3.62. So I'm going to explain in the next lecture the how do you interpret this value of Durbin-Watson statistic. What does it mean to have a DW statistic is equal to 3.62? We'll explain that. But before we end, just one point you need to keep in mind, and that is, look at this error. So look at this column for error difference squared and look at the column for error squared. So essentially you see that the error difference squared, I'm having one term less, whereas error squared, I'm having all the terms, right? All the terms corresponding to all the rows. Now, this might matter in when we have less number of observations, but when you have large number of observations, this will not be a very important factor. All right. So with this, we end the introduction to Durbin-Watson statistic. In the next lecture, we are going to explain DW statistic in the context of positive autocorrelation, negative autocorrelation. We'll also talk about we'll try to understand the values of DW statistic in different contexts. And finally, we'll talk about the limitations of Durbin-Watson statistics. Thank you.